So today we are going to talk about the general transport equation. General transport equation is an equation that can be used as a general to present all the transport equation or the governing equation or the conservation laws that we derived before to be utilized forward into other activities. For example, when we touch base with the finite volume method, we would like to integrate the conservation law. And it would be much easier if you have one equation that can present everything to explain what a finite volume method is. So far, we have three major conservation laws: the continuity, momentum, and energy equation. And we can write the continuity in a short format here. Which can simply written as partial rho by partial t plus nebula dot rho vector v equals 0. This is the continuity equation. And the general form of the momentum equation is partial rho vector v by partial time t plus v dot. This is nebula rho v, or we can write it down in the form of v dot nebula rho v. You can find both forms equal minus nebula p plus nebula dot mu nebula v plus the body force g. And the energy equation is partial rho e by partial time t plus v dot rho e, or we can write it down as nebula dot rho e v equal to minus p nebula dot v plus nebula dot lambda nebula t plus mu phi, the dissipation function, plus the this is actually the heat generation term or heat source term, plus any other kind of body forces like electric force or magnetic force. So these are the three equations that we derived in details: continuity, momentum, and energy equation. So the question is, can we build a generalized form equation that present all of them at the same time? And the answer is yes. There is a general form that can present all of them with a little bit of a change in one parameter. So let's look to this equation here. So I have, like sounds, we have the first derivative of time all the time. So we have a term that presenting the transient term, which is partial rho. And I'm going to call a general variable phi by partial t. This phi could be 1, as in here, right? It could be vector velocity, v, could be the energy, internal energy. So you can look into the first term of each one of these equations, and you can generalize it that way. And based on the value of phi, you can go between the continuity, momentum, and the energy equation. Then a second term that's related to the convection term can be written as nebula dot rho phi times v. So you can tell, again, if phi is equal 1, I'm here. If phi is equal v, because I have a couple of v's in here, it sounds like it takes me to the momentum equation. If I put phi equal e, it will take me to the energy equation. And the right-hand side can be simplified as nebula dot kappa nebula phi plus S phi. So that first term here in this equation is presenting the transient term, or the unsteady term. The second term is presenting the convection term. This is the diffusion term. And this is a source term. So if we would like to translate that, it's the time change of any variable phi, the time change of variable phi. This is presenting the transport of phi by motion of bulk fluid. So this is kind of energy carried by the motion of fluid. The third term here is the transport of the phenomena phi, or the variable phi, by diffusion. Don't forget that the word diffusion is simply called convection. So this is simply the motion of the molecules, not the bulk fluid, right? It's more by molecules. And the last one is actually the source term. It's a internal heat source. It's chemical reaction. It is whatever that source is. Okay. So this is what we call it, the general transport equation here. General transport equation. Let's validate the truth that this equation can lead to continuity, momentum, and energy based on the value of the general variable phi, or the phenomena of interest here. So for example, if I write down the equation at the top of a piece of paper again, partial rho phi by partial t plus nebula dot rho phi v equal to nebula dot kappa nebula phi plus S phi. So for example, let's actually put phi equal 1. Case number 1, I'm gonna put phi equal 1. Kappa is equal 0, and the source term is also equal 0. Let's see what's gonna happen to this equation. If phi is equal 1, I will have partial rho by partial t. Phi is equal 1 plus, now phi here is 1, so that's nebula dot rho v equal to kappa is the diffusion term is 0. This goes away, and the source term goes away, so the right-hand side is equal 0. What is this? That's clearly the same as the continuity equation. So if you put phi equal 1, kappa equal 0, source term is 0, that leads to the continuity equation here. So how we can use the general transport equation to reach to the momentum one. So that's, I'm gonna call that case 2. If you put actually the variable phi is a velocity vector, and you put your kappa, remember kappa is the general diffusion coefficient. So if we talk about heat or thermal, this would be simply the thermal conductivity. If we talk about fluid flow, diffusion coefficient will be simply the viscosity, right? If I talk about chemical transport, it's going to be the chemical concentration and so on. So in this case, I'm going to put phi equal V, and I will take kappa equal mu, since we're talking about fluid flow here. And I will put the source term is simply the pressure force and the body force. If I do that and substitute into the above equation here, what we're going to get? We're going to get partial rho v. I'm replacing phi with v by partial t plus nebula dot. I will have rho v, right? Which can be written as v dot nebula rho v, both are correct, equal to nebula dot mu nebula phi, and the source term would be minus output rho g first minus nebula p. Let's compare that to this equation here. This is the first term. Then we have v dot nebula rho v, and we have minus delta or nebula p. I have the body force, and we have the diffusion force. So I can drive the momentum equation from the general transport equation by controlling the values of the phi, kappa, and the source term. The little bit more complicated one is case number 3. And when we drove that general equation, it was obvious that we're going to use phi equal to the energy, internal energy. Kappa will be actually the thermal conductivity, and the source term will combine everything like the volumetric heat source plus the heat dissipation function term plus the other body force. And keep in mind that let's substitute, so partial rho E by partial T plus nebula dot rho EV equal to nebula dot K nebula E plus rho Q dot S plus mu phi plus K dot V. If you compare that to the energy equation here, so here's the first term. This is exactly first term, second term, diffusion term, and lambda is thermal conductivity. So both are same. Okay. Then here's a dissipation function, the heat source or the heat generation, volumetric heat generation source. This is the body force, and we are missing the pressure term, right? So that should be in the source term as well. So I should have that minus P dot nebula dot V is in the source term. So that's minus P nebula dot V. So this would come minus P nebula dot V. So again, this is just to show you by controlling these variables, you can simply bring in the transport equation or the conservation laws as needed. Okay. So that's a good finding here, to have one equation that can present the continuity, momentum, and energy equation. So when we start looking for the finite volume method and we start actually doing integration of that equation, it's going to be much easier than dealing with the individual correlations one by one. We know that we have the continuity, the 3 momentum equation, X, Y, and Z, the energy equation. So if you want to deal by integrating each one of them, it's going to be kind of a headache. But now we can deal with one equation. We do whatever that mass transformation that we need to do to it, and we know how to drive backward each one of the equation by controlling the variables here. So that's simply what we call the general transport equation, and that's conclude that section here.